Okay, hi everyone. Welcome to this talk from Lance Legel, and welcome Lance. Thanks for coming. This talk is being recorded and could be maybe posted publicly, so just be aware of that. Bit of background about Lance. Lance is a physicist and AI entrepreneur. He studied under Geoffrey Hinton in his lab. He's worked on planetary science for NASA. He's co-founded multiple AI companies, and he's here today to introduce DeepEarth, which is an open source AI architecture for planetary science and sustainability. So welcome, Lance. If you're ready, go ahead and get started.
Absolutely. Thank you, Patrick. Thanks, Patrick, for inviting me. Thank you guys for attending. Thanks to all the remote attendees. I recognize some names on the list there, and some warm welcomes for everybody. Looks like we have about an equal split of remote and in-person. I'm looking at this beautiful Space Needle in Seattle right now, speaking from the Allen Institute for AI, which I think every AI person I've ever talked with, sort of on top of Google and all these different companies, agrees that this is one of the top AI laboratories in the world. And so it's a huge honor, and really just, it's very emotionally inspiring to be here with you guys. So thanks a lot. I really, really appreciate it. So what we'll do is we'll talk about this DeepEarth architecture. The goal really to think of this whole talk is sort of a bid for collaboration. I think right now we are in the process of developing this model. So I think it's, we've trained and developed several parts of it. There's some things that we've seen that are really spectacular and you can use today in your modeling work, and other things that we're still in the process of fine-tuning. And so I'm just inviting collaboration to think of it from that lens, basically. So what we have here is just a beautiful little visualization of the planet and this 3D architecture, 3D coordinate system, this idea being that everywhere on the planet, of course there's a latitude, longitude, but there's also just a 3D coordinate in a Euclidean coordinate system where you go from latitude, longitude, the elevation or the depth, because this model could work inside the planet or outside the planet, and as well as a timestamp. So it's important to think of this as an XYZT model that has a continuous deep representation across space and time. And that really is the key innovation of this model. And so we'll dive into all of that. So it's a great pleasure to be here, so thanks. Okay, cool. So it's really important to say that this doesn't happen overnight, and this doesn't happen. It really does take a village to pursue these kinds of projects. This is a highly interdisciplinary model, and it's several collaborators from the University of Florida, several of whom are attending this talk right now, as well as from Stanford, University of Illinois, Urbana-Champaign, PhD students at the University of Houston, Arizona State University, and we go down the list from big tech companies who've been contributing through engineers who've either was one of the first engineers at Google DeepMind, also scientists from NVIDIA. There's someone who's currently working on AI models at Meta right now who's collaborating on this project. And I also want to thank the NSF Institute for Geospatial Understanding through an Integrated Discovery Environment, or iGuide, because basically they're responsible for actually putting a little bit of money into this project and giving us the compute and the support that we've needed to actually, begin to have these seeds be planted and be sprouted. So we also have this environmental side of these collaborations. So we have landscape architects and folks who are innovating in the field of landscape architecture who have recognized the power of having a model that can make ecological predictions at a landscape scale, and I'll get into that. But anyways, it's important to give thanks for other people here, and there is room for Allen Institute for AI right here. So happy to say that. So I want to start with where this was really inspired. And, there's many different types of researchers in this field of geo-AI and many different types of applications that we can pursue. And it's important to say that for my personal story and also for several of the collaborators who are on this project, we've been inspired by this goal and this mission of being able to increase the true ecological intelligence of the natural environments in which we live in. And so it's really fundamental and important to say that we're living in a time of what are considered to be some of the greatest crises of our generation. We're talking about the loss of habitats for biodiversity. We're talking about how do we even model and think about climate change at the scale of the landscapes that we're engineering so that we can actually engineer resilience into the planting designs and ensure that the planting designs are also functional for the environment and serve the people who are there. So this is sort of this multi-objective optimization problem that, eventually I started to realize these landscape architects and landscape designers, environmental professionals are solving what you might look at through a neural network as a multi-objective loss function. And the goal was, how could we directly pose that to a neural network so that it can begin to optimize ecosystem services, sustainability, and maybe last but not least, the beauty of the environments in which we're creating. So that's a landscape designed by this wonderful landscape designer named Pete Dolph. And it's important to say that basically, it's not the case that we don't know how to engineer these landscapes or we don't know how to create, let's say, flourishing, biodiverse, resilient ecosystems. It's just the case that there's very few people who know how to do it. And so the goal is to understand what is the kind of workflow in terms of actually the data that's being collected and the models that are being developed in this gentleman's head, who's a little bit older now even today. And here he is in a garden that he's completely designed. It looks wild, but that was a designed ecosystem. And so, the question is, how can you create AI that would be able to predict whether the plants would be flowering at that location, at that time of the year? What is the morphology of the flowers? What hummingbirds and butterflies do they attract? This is where DeepEarth was inspired originally. And I like to joke that we almost called this model Deep Bloom because this was where the inspiration was in the modeling. It just turned out that we ended up developing a space-time encoder that appeared to be far more useful than just solving the problem of flowering. So I did want to say one more thing, which is that typically what you get out of the landscape designers and landscape architects is what you would call a planting diagram. And it's important to think of this as a geospatial diagram, meaning this has a location on the planet which contextualizes the climates that this is going to be subjected to. And so you're ready right there connecting it with your climate models, but also there's microclimates. So you're modeling things like topography, you're modeling elevation, you're modeling the soil pH. So you're bringing all of these chemistry and physics fields to bear on a problem that historically humans are sort of solving in an old-fashioned, manual sense. And I'm saying this because the goal is most certainly to be able to get DeepEarth to model these types of distributions of plant species and how they're going to perform, and ultimately to basically do that in a way where we can just auto-generate these kinds of diagrams, and then maybe all of us can be living in a more flourishing, resilient, and functional, ecologically designed environment. So it's important to say that. So how do we get there? So at this point, we're sort of in this, situation where we need to say like, okay, what would be the deep neural network architecture, or what would be the scientific models that we would want to use to get there? So I thought I might sort of step all the way back at this point, and now we're actually going to talk about AI. So there's a variety of people attending this talk, including folks in biodiversity and ecology, and so for them, we got to address some of our motivations and where we're going with this. But I think now we're going to really focus on AI. And so, for starters, you can sort of look at some of these classic deep learning architectures like convolutional neural networks. And, it's important to say for some people who aren't as experienced in AI that basically you sort of start by understanding that a lot of the 2010s of deep learning was basically input some piece of data, let's say a picture of a dog, go ahead and learn all these connections just to ultimately have the model output one thing, which would be like dog classification versus cat. And the big idea is that all of these weights are going to the question of, is it a dog or is it a cat? And, so it was in 2017 that Quanta magazine, also a sort of nonprofit, AI-friendly group from the Simons Foundation, basically published this wonderful article that was saying, hey, look, all of these convolutional neural networks, and by the way, the vast majority of statistical models, period, are really destroying a lot of the information that's contained in your data. Their only thing that they're doing is sort of finding, let's say, all this information in the weights might be just going for your cat and dog detector to whether there's whiskers or fur. It's not really a model of a dog or a cat. And it's important to say that because most of the statistical models that people have been using historically, of course, even in deep learning, are sort of really not representing the data fully, which brings us to our first sort of architectural requirement for this model. So it's important to sort of step all the way back into history and say, well, I was talking with someone recently who was claiming that you can look into the early 2000s, maybe 2006, Geoffrey Hinton, and I wasn't in his lab directly, I was with a professor who directed him, so I don't want to overclaim anything. But basically, as far as what you're looking at right here is basically a picture of a cat, but it's not really a picture of a cat. This is from 2012, an article in the New York Times where they took 16,000 computers, scanned over 1 million frames of YouTube, and basically then had the neurons generate the most likely sort of pixels of a cat. And this was something that most people at the time didn't understand, most people today still don't understand, including in deep learning. But my point is basically, I remember seeing this picture myself personally at that time and saying, I'd really like to know what is going on here, because it looks like a cat, but it's not really a cat. Like how did this get generated? What is actually going on here? And so basically it was for me this question of trying to understand the paper by Andrew Ng and Jeff Dean behind this work. And this sort of led me in combination with the direction, from the neuroscientist who was saying, hey, he sort of gave me this very fortunate advice in 2012. He's like, there's this guy named Geoffrey Hinton. I want you to go study everything he's ever done. And I was like, how hard could that be? That can't be that hard, he's one guy. And then I'm reading all these hard math, hard statistics, hard biology, hard neuroscience, hard computer science. And I'm like, gosh, this is really hard. And I think I didn't even fully understand this stuff until maybe he won the Nobel Prize in physics. And I was like, hold on, wait, what did Geoffrey Hinton do again? And what were those restricted Boltzmann machines that won the Nobel Prize in physics? So this is an architecture for a restricted Boltzmann machine. And it's actually relevant because I'm going to mention it again and how I think we're going to sort of tune DeepEarth. But basically, what it is really, it's an architecture that you can apply to any data set. It's important to say for all of science, for all of engineering, that you can sort of take any input data, which is the bottom here, think of the E's as encoders, and think of the D's as decoders. And basically, any input data is sort of encoded into a sort of deep latent space. And then, of course, it's decoded. And the idea is that you're training the model to output the same exact representation of your input data. And by doing that, you're learning some compressed vector representation. And so this was in my master's thesis. And basically, I was also focused on large-scale computing of neural networks. I remember seeing what are the equivalent of scaling laws today. I don't think most of us had any clue about that, except Google. But basically, what I want to say is that it's important to say most of the architectures that we see, including in foundation models, are not necessarily doing this where they're sort of able to regenerate the data. And we'll talk more about that shortly. What I wanted to do is, just to make sure, and by the way, feel free to ask any questions, although I think right now we're still just kind of covering some basics. So I wanted to make sure that we understand that, okay, the whole goal is to get it so that you can build a neural network that can generate the original statistical distributions of the data. So it's important to say that basically, Geoffrey Hinton's guidance is you should be able to simulate your data in a way where you can sample from your simulator and the data looks indistinguishable from basically what the inputs are. So I wanted to start there. Okay, that's self-supervised learning. So the sort of next thing, and this is really going to be new for I think most people, unless you happen to have been working in 3D reconstruction, which most people in this field are not. So really, I think this is going to be the core innovation of DeepEarth. We sort of have called it Earth 4D because, and I'll get to that in a second, but I want to kind of right away, if you take away one thing, it's that Earth 4D is online, it's working, it's spectacular, and I'll show some results. And this is really how it works. I think it's helpful if you can have at least just a sort of high-level technical understanding. I won't go too deep, but the idea is how are we encoding space, and we'll get to how are we encoding time in a second. So this is from NVIDIA, and this technique was developed for photorealistic 3D reconstruction of computer graphics from camera photography. So take a bunch of photos and then learn to reconstruct the physical world. And it's really fascinating to say this because I was talking with a colleague at Stanford, and we both agree that we were sort of strangely obsessed with AI for 3D reconstructing the physical world with millimeter photorealistic precision, and we just didn't understand why. And both of us have physics backgrounds, both of us have AI backgrounds, and we were just kind of wondering why did we get so deep into 3D? And eventually it started to become clear that with these models, you can not just model the radiance or the light distribution, which is what they're originally designed to do, you can model the entire physical metrics. Any physical metric can be modeled with these architectures. So that's why I'm intentionally saying these architectures are ready to go, and they're just really general purpose spatial modeling architectures. And I'll show you shortly, spatiotemporal is where we extend it to. So multi-resolution hash encoding. So what is it? High level, you're basically creating a grid. In this case, think of it as you have a grid with, you're splitting up this into 3 by 3 for the red, and for the blue, 2 by 2. And the idea is simply, you may have several levels. So think of this as 2 levels. And at each node is a vector that you're saving a deep vector representation. This is the multi-resolution, and there's the encoding. I'll tell you about the hashing part in a second. But basically, the thing you need to know is that there is a fixed size sort of vector space, even as you potentially increase your levels and the number of nodes that you sort of want to model in theory, you could still fix your vector space, because what you get to do as you put, let's say, so many nodes here, where you're trying to save, again, think of this as occurring across the planet. So have your grid be across the planet, have your resolution space be at the scale of, let's say, kilometers and tens of kilometers, all the way down to whatever precision you have the compute to handle. But I'll describe how we have a hashing trick that basically allows you to handle much more entropy than you might otherwise be able to do if you were to just sort of naively put this into your GPU VRAM, basically. So the big idea is basically, at each coordinate there's a vector space, but what happens when you're sampling somewhere else, because you're going to be able to sample at any continuous point, which is sort of a feature of this model versus a lot of the classic geospatial models that have sort of binned precision. They sort of only go to 10-meter spatial resolution, as Alpha Earth does, and so forth. And in this architecture that we're presenting, you can have any continuous precision. And so it's a really big benefit of this, by design, so that we could, in theory, be working at sub-meter landscape scale with a planetary model. And so the way that it works is that you sample a coordinate, and then it gathers the nearest neighbors in your grid space, and it interpolates the vectors, basically. And so this is really important to just understand that basic, that's how you're getting continuous vector representations that are actually sort of responsive to what's being encoded at these discrete vector lookup locations. And sort of last but not least, you go ahead and you take each of your vectors that you look up at all your different levels. So again, you could have vectors encoding, let's say, kilometer scale, entropy and dynamics, as well as down to meter scale. And I have to give credit to one of the AI models that was like, yeah, that's going to have it be such that these climate dynamics are saved in the kilometer scale vectors, and your meter scale dynamics might have microclimate dynamics. And so you can just imagine how whatever scale of frequency the data is at, the model will sort of automatically learn to allocate to the scale where it's going to sort of, have a maximum entropy compression efficiency. And so basically, the simple thing to know is that you come through all of this, you have all of your levels, and then you just get this single vector. And so I'll just say right away, Earth-4D's default is a planetary scale model that if you don't change anything by default, it will run from 1900 to 2100. And if you do this, it will have good precision, and I'll show you. But basically, you'll get this 162-dimensional vector out of it. And you could do whatever you want with that. So you can put in any XYZT coordinate into Earth-4D, you'll get a 162D vector, and you get to do anything with it. You can put it through an MLP, you can concatenate it with other features that you have, and I'm going to go ahead and make a hypothesis. As a professor at Stanford University has said, we make hypotheses, and that's the currency here. My hypothesis is that Earth-4D will just sort of across the board improve most of the modeling work that you're doing. So that's my hypothesis. It's good to make grand claims and then be wrong. So basically, we're looking at this Earth-4D model right now, and it's actually a very simple trick that you sort of take the XYZ encoder that we just looked at, a spatial encoder, and I have to give credit to a project from a Shanghai AI laboratory that came up with this architecture called Grid 4D. And what they did was they basically took the exact same CUDA kernels that have been heavily optimized. They are very, very fast, extremely efficient, and they just copied and pasted it so that to include time, to have time be a first-class variable in your input model, and we'll talk about that in a second, basically they just create 3 different spatiotemporal 3D sort of grid spaces. So XYZ and then TXY, TYZ, and TXZ. And this sounds really hacky, and there's gonna probably be some better architectures in the future, but let me just tell you what you get. The big thing that you get, of course, is you have vectors coming out of each of these. When I mentioned the 162D, that's actually all of these combined. And what I want to talk about for a second, which is really crucial, is an inspiration for why we did this, and sort of validated by a lot of the results we're seeing right now. And that is basically coming from the field of astrophysics, you know, sort of being exposed to like Einstein's equations for relativity. One of the things that really was a key thing that I realized was like most of the sort of naive models of sort of space and time think of time as an independent variable, whereas in fact time is this transformation of space. And you need to jointly model those distributions. And so most of our architectures just sort of try to encode time, try to encode space, you know, hope that we sort of learn some connection between them. And instead, you know, I said, well, we need to jointly learn those distributions. You need an architecture that can just jointly see the statistics of time and space and not really think of time as anything different, except an extra dimension in space, maybe. And so that's where you have these sort of time XY, time YZ, time XZ inspirations. And yeah, I'm just happy to say you get this sort of full joint distribution of space-time continuously embedded into this architecture. So yeah.
So should we think of Earth 4D as a very good kind of positional encoder for space and time? Or
yeah, precisely that.
So the stuff like elevation map, weather that comes later.
So in fact, what we do and what there's a colleague at University of Houston who sort of will have it so that you'll just input, we've already coded it, like you'll input the latitude, longitude, we'll look up the elevation for you from a Copernicus global 30-meter map, basically. Or if you're in the US, we can use a 10-meter map. So we'll automatically look that up. But you might, for example, you might be dealing with seismic data underground or something, or some atmospheric data, and you'll go ahead and consciously, input your elevation or depth at that point.
I guess what I mean is the stuff like weather
Exactly.
come in DeepEarth, like after.
It absolutely can. Yeah, I mean, you can encode. Think of the. I'll be honest. I sort of had to rewire how I think about reality from this model. But you sort of want to think about all these things in some sort of same spatial coordinate system. So the weather, having its XYZ coordinates way out, you're sort of in the sky, and here we are, and we're in the same coordinate system as a lot of the climate data, basically, if that makes sense. And that's how this model learns. These are great questions because it is the space-time fabric. It is that encoding where, first of all, most of the model variables are going to, and second of all, which is the way that we're tying together potentially so much data in the multimodal space, and we'll talk about that. But it's important to say that a lot of these multimodal models historically, I would suggest, and by the way, I know there might be folks who built the Allen Institute's Galileo model here in front of me right now.
There are a few.
There are a few, yeah. So it's a great model, first of all, and I'm really excited to collaborate. And I think basically, I think this is going to be sort of, I think, an improvement on how we ultimately are sort of finding those continuous distributions in space and time, and it's all I really want to get out there, basically. So yeah, I think one of the things that I wanted to make sure, this is going to be super technical, but I think for the engineers, this is going to be very valuable. So basically, most people can't even see this, but you guys have your computers. So the short thing to really quickly say is that, so the sort of default Earth 4D resolutions, which you can change, you can define the number of levels. So I talked about how there's these multi-resolution hash levels. So the default that I've landed on that gets great performance that I think is going to work for most geospatial applications is 23 levels, where technically you go from a level that's encoding 800 kilometer resolution, there's a level that has 1 kilometer resolution, all the way down to 0.1 meter resolution. And temporal, you go all the way down to 15-second resolution. it's important to say that you don't just sort of get this level of resolution for free. Yeah,
How did you, like, how did you pick this?
a lot of experimentation.
Like on what, like what are the metrics that you used to
Yeah,
decide whether this was good or bad?
There was I decided to use Earth4D to try to predict. I decided, okay, what's something that has high entropy, high resolution? So ultimately, this Alpha Earth model that came out is a 10 by 10 meter scale global model with 64 dimensional embeddings, basically.
Yeah.
Packed a ton of stuff into it, and I said, well, what if we just have Earth4D try and predict the Alpha Earth embeddings on a real test set and evaluate that? And in this case, basically, it was just spectacular to see the error, going down below 4%. And here's just a look at basically the ground truth Alpha Earth embeddings projected from just like an autoencoder or UMAP into 3D. And you can see how we're learning Earth4D over time. And I was talking with a biodiversity specialist, and she was like, oh yeah, I can see all of a sudden it becomes like purple, later into training. And so it's wrapping
I'm
around.
kind of confused. Why is this, like, what does this offer other than like just using Alpha Earth directly? Because this is just like, in some ways, just memorizing what Alpha Earth is.
Yeah, think of this as sort of a debugging test. Like, indeed the question that you asked was how did you tune those parameters? And so to get it to successfully predict Alpha Earth, I had to I was defining the levels to do that. In the beginning, it didn't work properly, just like every deep learning system.
Gotcha. And this, like, what do you want it to be, the system to be able to do in the end, that you believe like this is like a correlated task to whatever you want? Because like obviously, as you said, this is just like kind of a smoke test.
I think basically the short of it is, this is sort of fast forwarding through some things which I'm totally fine to do. I'd rather this being an engaging thing. So basically, the core of it is that you sort of take this Earth4D architecture, which is down here. You allow your model to potentially take in any number of modalities, from vision systems and language systems, and really just from any encoder and any data set that you want. So you should be able to sort of literally throw in all the data from anything. And the thing that I would challenge everyone is to sort of figure out a spatial and temporal coordinate for every piece of data that you have. And I think as soon as you start to force this exercise, where you're saying, hey, that data, that video, that, whatever, that sentence came from somewhere and it happened at some time. It turns out that you can sort of natively take all of your modalities and project it with the sort of Earth4D embedding, and you can do your sort of multimodal fusion where the model is aware of you. It uses that Earth4D sort of embedding tied together with all of your data sets to sort of learn how to inductively infer, let's say, missing parts of your data sets, basically. And so the big goal is really, you train a model with like mass auto-encoding across your data sets, but ultimately, while you're using this in a sort of a training environment where you're predicting held out ground truth information, like covering up an image and reconstructing the image, or covering up the description that a hummingbird species is flowering a particular plant species and filling it in. But of course, the value is in getting a system that can infer this for the very sparse data sets that we have in a lot of the things that we're dealing with. Most of our ecological data sets, we have just a few observations here and there of the plants across time. We want to know densely, what these habitats are and what they're doing.
So, yeah, I guess this kind of, I'll start with one question, is that like, going back to like, if you want these like observational things to work sparsely, why is like linear interpolation a reasonable thing to do? Because I can imagine that like at certain scales, it might be like quite stepwise, like the changes across things.
I agree with you. It's linear interpolation, concatenation is not the best thing, right? I mean, I'm just agreeing with you right away. I think you've nailed it, and I think it is tricky to sort of tune all of that together. Meaning, there's going to be. It turns out I've been training some of these end-to-end models, and it's sort of not ready to show the full results yet because I'm literally debugging certain things still. But what we're seeing is that I wanted to make sure that you could sort of have a learnable mapping from each of the encoders to the multimodal fusion, and that would be these sort of dataset feature decoders is what I'm calling them. But the whole point is that instead of just sort of concatenating your embeddings, ideally you're learning how the embeddings, you're sort of doing cross attention, for example, between your embeddings from this and your embeddings from that. And it turns out it's a little bit difficult. I'm not gonna say it's an impossible problem, it's just something that we're currently working on.
Okay, and so just to understand, like where you're at in the project is you've thought of this architecture, but like training models end to end with like these different input datas is like a next step? Is
I think
that,
that's
am I correct?
currently like
Okay.
last night seeing models training and seeing basically some of the embeddings collapse, which is a known challenge with multimodal. And so we need basically regularizers, which is a very common thing. But I've been seeing losses declining for multimodal for the end-to-end architecture. And it's like really exciting, and then you're watching as the model like collapses into the ground, and you're like, okay, let's try, let's make that Ferrari engine, not blow up this time.
Like what are the like kinds of tasks you're using to see if, let's say like
That's
the
a great
loss
question.
going down is like correlated with real performance?
I don't have a slide for it. It's a great question because, actually I don't have a good slide for it. I'll just say that I've recently constructed a data set for predicting flowering, and it's 500,000 observations from sort of, I guess, 5 different types of modalities. It's like iNaturalist images, it's species embeddings from a text embedder of the species names called BioClip, which gives you these really good species embeddings. It's the sort of, I'm actually concatenating or combining Alpha Earth into that model. I sort of see it as like we shouldn't be competing, we should be joining.
Sure.
And so Alpha Earth learns like climate and all these different things automatically. Could be Galileo. And so I think ultimately you're taking, I think the sort of proof of concept model that I have right now called DeepEarth flowering v.1 is these 5 modalities predict for any location, for any time, for any plant species, is it flowering, yes or no? And it's for any angiosperm flowering plant species.
So for that, like what input data are you using?
Yeah, it's like 500,000 observations, and when you sort of break out each of the modalities, it's like 2.5 million approximately.
Like which modalities are you using? Like if I wanna I have a location I care about, is it like which data are you grabbing? Is it like
Yeah,
samples?
the data is
it
mostly
aerial?
iNaturalist. It mostly comes from iNaturalist observations. And I think that's the best data set that we have actually.
Okay, so it's like predicted from like ground images.
Exactly.
Okay.
Yeah, every image has a space-time coordinate. Every image you can get vision embeddings from, and basically you also know the species, so that ties you in with all these biological, embedding models as well. So I think iNaturalist is our best data set. And generally speaking, biodiversity data sets, since there's a lot of other ones. These are great questions. Okay, well, I'm gonna make sure I don't go over time first of all. So we're 11:35, we're pretty good right now. But please keep asking questions. It's really fun to kind of engage with you and understand. So I think what I'll do is just make sure we're not missing a few key things. So we'll just step back real quick. I think we're pretty good. So, we sort of ran through multimodal real fast. I just wanna make sure that for folks who are sort of still wrapping their heads around things, because I think not everyone is sort of gonna be up to speed. I think basically, the general principle of multimodal is that instead of just masking your single data set, you're gonna be masking several data sets. And the idea is that you have an embedding space where the encoders from data set A and data set B, in this case, you have an image of iNaturalist of a redwood forest in Santa Cruz, which I've personally visited, it's very beautiful. And basically, you have another satellite image of that exact location. So now you're taking a totally different data set, same modality of images, but completely different distributions, and you're jointly encoding them into a shared embedding space, and this is a cross-attention layer, which we can thank OpenAI folks for coming up with that. And then you're of course trying to decode, but the big idea is that you're using information from dataset A to reconstruct dataset B, and vice versa. And it's just important to say that this is sort of like, I think what we're seeing, the level of what is called induction, which is inference with high uncertainty with language models today, where you're asking it to let's say code your architecture, or you're asking it to solve a puzzle, is really spectacular, right? It's really amazing. I think basically with the data sets that we can actually encode with these kinds of models, you're gonna get similar levels of induction, where basically you're gonna be like, look, I have this, temperature data set, I have et cetera, and you're gonna feed it all into the model, and you're gonna give a few sparse observations, and I think it's gonna generate the ecosystem properties with high accuracy once we fine tune all these things and get all the right data sets in there. And that's a big claim, another hypothesis, but the point is that it all comes from this idea that your embedding space is sharing information across your modalities, and the whole model's output is the original data set. And so the training task is identical to GPT, where you're hiding language with GPT, and then you're reconstructing language. And it's important to say that, in my opinion, this is my humble opinion, while there are many great loss functions for training foundation models, in my opinion, the only sort of one that is going to get you to GPT level performance for your data set is masked reconstruction, because you're forcing the model to learn to generate the statistical distributions. If you compare that with like contrastive learning, for example, what ends up happening is a lot of those other kinds of models, again, come back to that bottleneck where you're just sort of shoving your embeddings into different spaces and you're destroying your features, but you're meeting the training objective of, let's say, distinguishing concept A and concept B in your embedding space. And I'm saying, well, that's nice, but the real architecture that's going to get you to something that's simulating the universe is going to be that you have to recreate the universe when you cover up the data sets and force your model to auto-encode that. So I'm just happy to strongly reinforce that. Okay, I wanted to say one thing about this as well. It is.
I have a question.
Yeah.
For that claim, why do you believe that? Because there's been like a lot of different things where like there's like at first there's like I guess a big space of like what kind of masked reconstruction of like if reconstructing pixels or reconstructing in the latent space is better.
Right.
And there's also been stuff that like use like some form of contrastive loss that have been shown to work really well on like a wide range of tasks. And so I'm wondering like why you believe that so
I
strongly.
think these are great questions. I think I want to say the first thing is that I don't think contrastive loss is useless. I think I would say there's a lot of applications where it's powerful and it's effective and sufficient for what you're trying to achieve. Classification is a great example. If you're trying to achieve a classifier, contrastive loss is great. The Dino V3 models from Meta for vision were trained with contrastive loss effectively, and they're really wonderful.
Not really. The Dino V3
And it's like a
also.
teacher student,
Yeah, but they also have like one of their loss is like a local, like sort of like not reconstruction, but in latent space, they're like
Right.
classifying like from a set of prototypes.
No, exactly. Yeah, I think what you're saying is really beautiful and important to understand. So basically, you can reconstruct the raw data sets. To be totally frank, I don't have the compute to do it right now. I don't have the compute power personally, or with my collaborators that hasn't been fully extended to me. But my point is that, so right now all of DeepEarth's training and testing is in embedding space. So basically we're only reconstructing embeddings right now, which of course, you sort of get past that original encoder problem of basically, needing to build these very expensive encoders. The embeddings are often smaller in dimensionality, and so the training is much faster. But I wanted to get at this idea that when you're reconstructing an embedding space, it's an idea from Jan LeCun. Yes, it's a sort of much more constrained problem because your embeddings typically, depending on how they were trained, comes back to how your embeddings were trained. Your embeddings are typically smoother than the real world. And so what I would say is that you want to reconstruct embedding space. It's going to help you. It's similar to like a variational autoencoder. But what I'm getting at is that I do believe ultimately you really want to reconstruct the raw data sets. I don't think there's going to be another metric that you're going to know for sure that you have a simulator, because otherwise you're sort of, you're training it to do certain tasks, but can you really generalize it to truly simulate the distributions, in this space-time?
In the simulation though, or isn't the end goal per se, right? Like we want to be able to use are you imagining, or is that the end goal, or is the goal to like take the encoder from this and like fine tune it for the other tasks? Which is the
great
goal?
questions, and you're sort of leading me into great places. So 100%. The goal is both.
But that was an either or question.
Well, they're
so I'm
both.
confused.
They're both, and one
Okay.
comes before the other, right? So first you train the foundation model, which is literally just the simulator, and you can do this, by the way, for many different data sets. It's not really going to be one DeepEarth model or one, collaboration. It's going to be this sort of similar architectures being applied to many things. And the point is that it's valuable to have that. Sometimes people just want to know, what does your model think is happening over there? If I put a plant in the ground, is it going to be flowering? Okay, but what you're getting at is going from the GPT to the chat GPT, right? It's basically, you train GPT on a trillion tokens or whatever. Okay, it's nice that this thing can just autocomplete words in a sentence. It's not useful. It's really not. So, I'm suggesting I think simulating the environment is useful by itself, but I actually would suggest the fine-tuned models that you can get from these architectures. I think that's where the meat of the value creation is going to happen. That's where the iceberg of value to be created here is, because you're training these foundation models, then you can fine-tune them for, let's say, optimizing to create the most resilient planting design or whatever you want to do, basically. Does that answer your question? Is it fair? One comes before the other as well, basically.
Yeah, that's fair.
Okay, hopefully I'm not upsetting people.
No.
Okay, good feedback. Okay, great. So I did want to make sure I stopped here for a second because I was sort of like spending a lot of time thinking, oh man, how am I going to basically solve this problem of, putting all of these tokens together and, what is the architecture for this multimodal fusion? I really don't like creating things from scratch. Like if someone else has done it a lot better, I'd rather just give them honor and incorporate it. And so this is an architecture that I realized has 2022 DeepMind Perceiver IO. They basically solved this problem of sort of taking what looks a lot like a context window for an LLM, and basically this is a single token. So these are dimensions of your token. And in this case, basically they're sort of saying, hey, look, you can put your video embedding, you can put your audio embedding, you can put some label of what is happening in that video and audio. You can jointly learn to reconstruct with a masked autoencoder with this architecture. And they've made it very efficient for being able to basically query it with a decoder that's only querying the masked component. So that's very nice. It has built-in cross-attention and self-attention as well. And you can sort of configure this, and they sort of have demonstrated that it has just basically general purpose learning capabilities across all kinds of data sets. This actually came out around the same time that I think like the GPT-3 and 4 models really took the world by storm. And to be honest, I think that this architecture sort of got a little bit overlooked compared to what happened. So I'm just saying, I think this is good. This is correct in my opinion, and I think we can use this in DeepEarth, but I think more generally for any sort of multimodal autoencoding problem, you can use it. But we are going to basically put Perceiver IO right here. So I've been testing it. It works, but yeah, like I said, I'm still fine-tuning. Okay, so I mentioned there's some tests. I do want to make sure I leave time for questions. So I'll try to finish up within 5 minutes, and then we can get you guys out of here for lunch, basically. Okay, so I was mentioning Alpha Earth, like when I started to come out with the DeepEarth architectures, I know we have a lot of folks working on foundation models and so forth. This was sort of a drop. This was sort of like an exciting moment to see folks release this model. And just want to say, it's this beautiful 64-dimensional embedding. I do want to say that it's available. It's easy to download. You can, just like Earth 4D, you can sort of plug and play with this architecture. And I just wanted to make sure that I communicated for everybody, including folks remotely, that basically it includes RGB and thermal satellite imagery. It includes basically synthetic aperture radar, digital elevation maps, LiDAR, climate, gravity, land use, land cover codes, as well as Wikipedia texts that have geospatial coordinates. They've projected it into this embedding space, and they've taken biodiversity observations from the Global Biodiversity Information Facility and had their embeddings align with the embedding tokens of a Gemini 2.5 model. This is a beast, and we've seen this architecture, we've seen these embeddings when I was in Boulder, Colorado with the NSF iGuide program. All these teams put Alpha Earth into their model, just sort of plugged it in with their other sort of things, and the model got better. So, you're looking for these general purpose AI things in Geo, and this is one of them. And so, I was mentioning, okay, so we decided to see as a test if we could learn it. I already talked about this, as well as this. And, I just want to say Alpha Earth is basically going to be plugged into pretty much everything by default in DeepEarth as well. We're just going to kind of pack all that. And then we don't have to go learn, Sentinel-2 again. Basically, we can just assume that they've learned it properly, at least for now. So I just wanted to show you a few more results. So one of the reasons why I'm here is with Patrick, we were both kind of getting into modeling of this data set. live fuel moisture content across the country. These are their observations of how much moisture is in the plant species. This is for fire ecology. Currently, I'm engaging with folks to help solve this problem, potentially with the city of Berkeley, California. They're looking for a solution, actually. And basically, it's just interesting to say that you have this sort of latitude, longitude, sampling date, sampling time, live fuel moisture content value, how much moisture, and then the species. And so it's cool to say that Earth 4D basically, without any ecological variables, just those coordinates basically, is getting a very good precision. I think Patrick, for the first time, is seeing these results, so he's getting to know his models. This is in the LFMC percentage space too. So if it's LFMC 200%, the error is 15 percentage points actually. So it'd be 215. And so you can see that we're generally doing quite well. We had to give it a species awareness. Turns out you can just give it a vector that you sort of have an embedding for the species, and you concatenate that with whatever else you want, and then you can learn the species. It's necessary because you have degenerate points basically.
So this model just puts in the coordinate and then predicts the LFMC value?
Yeah.
And then how did you split the train and test set?
Yeah, great question. So we had 3 different types of tests. One was a true spatial holdout, another one was a true temporal holdout, and then the third was randomly distributed with the rest of it. And this long story short is that the model basically did really well across all of them. I think sometimes in certain spatial circumstances, there's no other training evidence, so the spatial holdout does not as well, basically. The temporal holdout generally does great. We held out like the last 6 months of the data set, basically. And this is included in this visualization, so it's basically somewhere over here. And what you see here, it's kind of hard to see, but basically it's, the red is the ground truth distribution for the month of LFMC values that were observed. The blue is the predicted distribution. It's also just cool, I intentionally put this in here to see that the moisture levels are rising in the summertime, basically, as you would expect. And so just nice to see that not only, we're basically reconstructing the data. This is all tests, basically. So really good results. And yeah, this is just making sure Earth 4D is working properly, basically. Okay, so we're gonna sort of switch gears, and I think we'll move to questions. I just did want to say real fast that, yes, it's a work in progress. I'd rather, present it that way by collaboration than say, hey, it's all done and, it's all over. I think this is going to go on for multiple years, and I hope we secure lots of funding and stuff to do this work. So yeah, I'm really inviting folks here and remotely. I just want to say a few challenges and intentionally make that the point of collaboration. Basically, multimodal loss regularization, not trivial, happens to be what I was trying to debug last night, so I think we'll get past it real fast, but just throwing it out there. Bayesian distribution estimation, I think it's really exciting to say that the architecture should be able to explicitly output uncertainty, and we've seen sort of ways to do that in a cross-attention space, where basically you can sort of have your spatial embedding, your temporal embedding, and your data embeddings, and because you're doing cross-attention in embedding space, basically you can, from that sort of cross-attention layers, you can implicitly be mapping the distributions back in your original data space. So you're doing cross-attention in embedding space, and you're able to then learn some sort of a gate to predict the probability distributions in the original space, but we're still at early stage on this. I do want to say scalable computing infrastructure. A lot of colleagues that are on this call, let's say from the University of Florida, they've got great stuff from NVIDIA these days. I know you guys are working with great things, so it's a problem. Right now, I literally did all of this work on a 24 gigabyte GPU, just to tell you how humble the origins are. And it's exciting, because imagine what happens when you start to increase the spatial precision. We literally just add more levels, increase the hash encoder, precision. It's quite exciting. So you guys can be running some of these first tests. I intentionally wrote this as foundational modeling. I want to make sure, and then we have organizational integrity. I just want to make sure that you guys understand, first of all, this is an open source project, and the goal is to support potentially, maybe hundreds of different, research and development projects across science, engineering, design. So I'm just kind of encouraging folks to consider this as a challenge and a focus for how do we sort of architect and move forward together. So that's where I'm going to leave you guys, and just saying thanks, and please, reach out to me by email. Pretty much most people have an email already. So anyways, thanks a lot. I appreciate it. Okay, yeah, so we've been asking questions the whole time. Thanks, Dan. Daniel's got a good virtual game he's throwing the. Anyways, we've been asking questions the whole time. Folks remotely are also welcome to ask questions. You can just speak up and you're gonna come through on audio. There's actually 15 remote folks as well. So anyways, just feel free to ask any questions. We're here for another like 5-10 minutes. So.
Yeah, I was wondering about the modalities that you're using for the training right now.
Yeah.
Yeah, you had that diagram showing the model one where you had the Earth 4D. Yeah, that one.
Sorry, trying to navigate there, right?
Yeah. So what you mentioned one of them in addition to the Earth 4D kind of positional encoding is iNaturalist. What other modalities have you thrown in?
Yeah, it's a great question. I think the short answer is iNaturalist observations, where I think of that as it's actually relevant to say the token itself, we're feeding in a dimension for the dataset, for the modality, and for the encoder, 3 different things. And so the dataset of a lot of this origin is iNaturalist. I think technically there was another dataset that I've considered recently called the Global Biotic Interactions dataset, which has pollination interactions. But I'm not going to mention that. I'll just say it's all iNaturalist, and the modality is either text or images. And the encoder, so we actually did 3 encoders for this on this sort of first model that I have a data set that I can hand off to folks and can run on. And it's basically BioClip, which we run both the iNaturalist images through and the species taxonomies through, all the way from Plantae down to the actual species name, because this is how they trained it actually. And it was trained with contrastive loss to sort of put the species so they're taxonomically close to each other in the embedding space. So that was done with the same encoder. I should have put the BioClip. It was originally visualizing the embeddings, and basically the vision embeddings of BioClip and the language embeddings of BioClip, they have a nearest neighbor correspondence, but the vision embeddings cluster in one space and the language embeddings cluster separately. But if you put a picture of an African elephant and then you ask what the nearest neighbor is in a set of text that you encode, African elephant text among all of your text nearest neighbors will be the closest. And this is because some of the dimensions in that embedding space are sort of mapping and the other ones are not, basically. So BioClip, Alpha Earth for every one of those observations, Earth 4D. And I wanted flowering, so I'm happy to say there's a collaborator from University of Florida who worked on a model called PhenoVision. It's a 98% accurate vision classifier for flowering for my naturalist images. And basically we ran that on a total of 3 million iNaturalist images, basically is the size of the data set.
So these would end up being at the same XY
Exactly.
ZT,
That's
but just
precisely
different, another
correct.
embedding.
Yeah.
Okay.
Yeah, that's precisely correct. And so every one of these, so I literally just didn't have time to sort of show a nice diagram of what our token structure looks like, but basically it sort of looks like, each of these tokens is, modality, data set, encoder, space-time, and data embedding combined into one thing. And so basically you can think of it as if you have, let's say, 500,000 unique space-time coordinates, which we do, and you may have 5 sort of unique combinations of modalities and stuff. You might have 2.5 million unique rows to train on, basically, if that makes sense.
And what's the Z for the Alpha Earth?
The Z for Alpha Earth, there is no Z for Alpha Earth. It's just latitude, longitude, and the year is what you get, is how you query Alpha Earth's embeddings, basically.
Okay, so in your embedding, that's kind of.
We use Earth 4D, right? So the Earth 4D will take the XYZT and encode that, and so we have Alpha Earth and Earth 4D.
Okay, I see.
Yeah. Cool. No, that's great questions. Okay, any other questions? Any remote folks have any questions? Still got 4 minutes, so. Yeah, it's like, I'll take one.
When you apply this, I guess what's the idea for applying the model later? Would you, well, A, is the idea similar to Alpha Earth where you just eventually want to get an embedding that people can use in their downstream tasks? And then B, if it is an embedding, then are you, like, will you just use the Earth 4D, can you just use the Earth 4D portion of that pipeline where you
Yeah, exactly.
feed it into the pre-trained model and get something, or when you want to do inference, will you have to have all of them?
No, these are wonderful questions. So the answer is it really was sort of envisioned as something that you would train it on all the modalities. It would leverage all of your other modalities that you don't really have in abundance. And then because it's literally designed to work properly with full masking of potentially all of your other data sets, the beauty of the simulator is it's mostly done through masking, and your queries is just really masking in different ways. You basically end up, you can just give it your spatial temporal coordinates and mask everything else. And you might only query it on some particular mask basically. But yeah, it's really fascinating to say that it's designed to work with. I think what you said was also very beautiful. Of, is it like Alpha Earth where you might get a 64D embedding for everybody? The answer is 100% yes. I just think that maybe unlike Alpha Earth, I mean, maybe we'll have a general purpose embedding once we all decide to put a ton of compute, but we don't. Even I wouldn't suggest we go for that first. The first thing we would go for are sort of domain-specific models, basically. And so I can tell you 3 of them that's on my list right now, and you guys can maybe add a 4th, or you can collaborate on the 3, is sort of flowering, predicting flowering for any plant species anywhere, basically anytime. Predicting pollination, predicting the distribution of the pollinators, the butterflies, the bees, the birds that are actually going to show up for a given plant species at any location at any time. So it's kind of this hard biotic interaction modeling question, where's the pollinator migrating, all these things. The last one that we also have had traction with, and it's partially why we're here, is this predicting of fire ecology. And so we're committed to sort of seeing those models through as our first models. There's probably hundreds of models that could be developed, and you could imagine an open source sort of protected, set of weights that people can download, and we sort of curate and quality control them and these kinds of things. I think it's really exciting to support lots of scientists, engineers, and designers worldwide with that kind of framework. So, thanks. Yeah. Okay, if there's no other questions, I can cut it off. We're pretty much at time, so I'll just say thanks for everybody. Thank you guys so much. I really appreciate it. So it's been wonderful. Thanks. Nice. And we can stop.